unfortunate case is that even when his eye is relaxed, it's too strong. How much too strong? It's 2 diopters too strong. The consequence of this is that this person has a shorter far point. And again, we can do the calculation. The nice thing about using optical powers and inverse quantities is that you don't have to deal with reciprocals of reciprocals. But we can always solve for f if necessary. Good morning. So, you weren't here on Thursday. I'm not sure if you know exams on Thursday.
Yeah, I know.
So the shorter far point, so 1 over O now, which again is the far point, would be 1 over f relaxed minus 1 over the eye's image distance, and we'll assume for this case that it's 0.018. Keep life simple. Again, I can continue to change these things. So what we're left with then is plus 57.56 inverse meters minus, if it were healthy, it would be 55.56. Therefore, it would be off by, it would have a value of plus 2 diopters, which would imply a far point of a ghastly 0.5 meters. So there's a person with this extreme excessive eye optical power, if you will, where the eye has too short of a focal length, even when it's the most relaxed, means that you can really only see things effectively with clarity at about a half a meter away. Probably pick up objects up to several meters away. You can figure you can fill in the gaps, but in terms of clarity, it sort of stops it. Okay? So the question is, or the dilemma is then, how do you fix it? How do you give this person as close to normal, healthy optics as possible? Well, the easiest thing to do when you see it like this is to say, well, if I knew this value and I knew that it should be this, it's just 2 diopters. All I need to do is subtract, figure out a way to subtract this value, or I'm sorry, the difference between these, to get your eye correction. So to correct for this, again, it's distance vision, but to correct for this, the optical correction and by the way, it is just happens to be what the far point is. If you knew what that was, and you could figure out what that was. You can think of it in one of 2 ways. You could think of it as what the corrected value is, right? Difference is always final minus initial. So in this case, what we have is we would want the optical power corrected. Whatever that is, that's what we're looking for. But we have to subtract from that what it currently is. Okay, so this is what it is. This is what we want. The difference between the two is going to be the correction. And in this particular case, it would be 55 minus 57. Backwards, because we actually need to subtract that optical power, right? So we have 55 point, it's a plus 56 minus 57.56, or negative 2 diopters. And that's actually pretty common eye correction. Typical eye corrections, most eye corrections are between about minus a half a diopter and minus 2.5 diopters. That's almost where everybody is, 80 or 90%. Then we have extremes, or we have people whose eyesight is just off enough it bothers them. So this would be the correction. But if you notice carefully, it's just minus the inverse of the far point. So this would be what the eye correction would be. Or, not eye correction, but this would be what your eye prescription would need to be. Give or take that little distance from the eye. So for a contact lens, it's probably the best example. Now, just as a little side note, typically, at least from a practical perspective, we're not going to be optometrists necessarily, but from a practical perspective, when you get a prescription, it's usually to the nearest quarter diopter. So if you're within a quarter diopter, you're close enough. So typically, the actual correction is given in 0.25 diopter increments. That just makes it easy for lens manufacturing, right? There's the engineering question, if you will. How do you make it practical so you're not customizing every single individual? So that would be how you would correct distance vision. Now, the other case, I think this is what I talked about before. There's two ways of looking at this. Okay? Both of them are interchangeable, but they're the perspective. Sometimes it's helpful to think of it one way or the other. The first is this particular person, because of this fixed distance, the assumption of this fixed distance means we can only see this far. Can't see beyond whatever this value is. Right? Now, the counter perspective to this is to say, where do you focus an image that in fact is at infinity? Okay? We know what the relaxed eye's optical power and focal length is. Where do you focus an object that is functionally a long ways away? Doesn't change how you calculate the problem, but we might just think, how does this uncorrected eye focus a distant object? And again, we just use infinity to indicate large compared to 2 centimeters. In other words, what is the image distance? Where is it? It's not going to be on the retina, it's going to be somewhere else, right? So if we calculated 1 over I, now this is the uncorrected, right? This would just be for this particular image distance. We would take 1 over F relaxed, now it's uncorrected in this case, and we would subtract from that 1 over infinity, which is going to go to 0. So we're left with whatever this value is, and we already calculated that. It's plus 57.56, or the image location for this particular image object, excuse me.
The one about 55.56, the healthy one?
No, this is not the, I'm continuing that
Okay.
one.
Okay.
I'll explain why in a moment. So we take the 57.56 and take the inverse of that then, and we get about 0.0173 meters. So the other perspective of this is when people are nearsighted, when they look at far, far objects, they physically focus them in front of the lens, or in front of their retina. So what should be focused here is in fact focused here somewhere. And that eye value is off by not even very much. We're talking a millimeter or less. That's enough. So this optical correction we calculated to deal with distant objects is to in fact take what their uncorrected focus distance would be and put it where it's supposed to be, or unfocused image distance, uncorrected image distance, and put it at the retina where it's supposed to be. And the way I like to think about it, and in a way it kind of drives optometrists nuts, is another way of thinking about it. It's like taking objects that are at infinity and physically placing them at your far point, optically speaking. Because once they're at your far point, and that's what your eye's far point is, then you can focus them on your eye. And your eye adjusts that perspective. It scales everything to that, if you will. So that's sort of essentially what happens. So like I said, one of a couple different ways of thinking about it. Taking distant objects, putting them at your far point, so you can focus in on your image because your eye has a fixed, relaxed focal length. Or alternatively, taking a distant object which is focused in front of your lens or in front of your retina and push it back. Either way, what you're doing is you're decreasing or diminishing the focal power, the optical power of your eye, or you're increasing the focal length. In other words, it's too steep, too short, so you got to figure out a way to contrive it to lengthen it a little bit. Now, and then the inverse would be true with people that are what we call farsighted. When people are farsighted, we say they are hypermetropic. In other words, their eye has, it sees beyond infinity, or hyper, so it sees, distance is shorter than the far point, if you will. It's hyper. As opposed to hyper means too far. So you're seeing beyond the normal line. Okay. And so very briefly, I'll leave this little part here. And look at what happens when we have a person that's far-sighted. Okay? Now this one is crazy. We're going to do this problem backwards. I remember this always made me think very strange. I'll use a real example. I had this girlfriend in high school. And, well, when I met her, she wore contact lenses, so I had no idea what, how good or how bad her eyesight was. And one day I was over at the house hanging out, and lazy Saturday, she didn't bother to put her contact lenses on, so she put her glasses on. It was like taking two magnifying glasses and putting them next to her eyes. I mean, these were like serious Coke Bolly looking things. It's like, wow. He had a really extreme prescription. Now, unto itself, okay, you need eye correction, no big deal. But here's what was weird about it. She took her eyeglasses off. She could see just fine. How the hell did that happen? How could you have eyesight if we had the inverse? If we were nearsighted with the same relative correction, we'd only be able to see about from this far away with focus. So this was absolutely crazy. I could never figure it out. But let's sort of think about what would be the reasoning behind this.
Does she have trouble seeing up close, but she can see at distances?
Yeah. So let's look at a person with eye correction. Of plus 6.5 diopters. So now we can just sort of go back through the same sort of information. I'm going to ask two questions. What is the relaxed focal length of her eye? And what is her far point? Now this is kind of a weird one. I don't know if we can actually calculate the far point because it's so strange. Okay, so to figure out what her uncorrected eyesight is, or at least her optical power. Again, the only reason for using this, why I like to talk about optics in terms of sort of this optometric, ophthalmologic language, is that the math is easier. You don't get lost in the inverses. But it's the same problem. So the uncorrected eye is basically going to be what it should be corrected. But we have to subtract from that the actual correction itself. And we know what the correction is. So for correct eyesight, and again, we'll use a standard image distance, retinal distance of 1.8 centimeters. So that being the case then, the corrected eye should have a plus 55.56 diopter optical power, and the inverse of that would be this number here. Now we subtract from that plus 6.5 diopters. Now we're going to have a rounding issue there, so because this one is, well, this should be okay. Take a negative, so something like 49.06. So that would be your optical power. Now, so without even doing that, we might say immediately, if you've got plus eye correction, and this, by the way, is true even with reading glasses, what that means in general is, under the conditions that you're getting those corrections, it means that your eye is not powerful enough. In other words, the focal length is too long. And so you have to shorten the focal length or increase the optical power in order to see normally under whatever those conditions are. So clearly this is 6 diopters below those. So we got to figure out then from that, well, what does that correspond to in terms of optical power or in terms of an object distance? Now this is kind of bizarre. I don't remember, I've forgotten. I didn't do this calculation for a while, but what would the far point be for this particular prescription? One over O far would be equal to 1 over F uncorrected. That's this value, minus 1 over I, or 49.06, minus, again, we've got this number, now this is bizarre because it tells us that our inverse far point is a negative number. Again, we come back to negative 6. And that corresponds to an optical far point of negative the inverse of 6.
0.5. No, inverse of 6.5.
Oh, I'm sorry, inverse of 6.5. You're right. Forgot I put that in there. I don't know what that number is.
0.15.
What the hell is that?
It's on the other side of the retina, so that's where the convention is with the negative. It's positive is in this side of the retina, and negative is on that side of the retina.
Yeah, is that bizarre? But what strange about this? And this again, this is in a sense a reach of perspective or interpretation, but if the object distance was, or the far point was infinity, what would 1 over infinity be?
0.
0. How does this compare to 0? It's below 0. So there's no such a thing as something being farther than infinity or beyond infinity, but in a sense, it's kind of like having a focal point, or a far point that is, or exceeds infinity. It's on the wrong side, so I mean, how can that be? But think about it in terms of any other numbers. 0.5 compared to infinity. 1 over infinity is smaller than 1 over 0.5. We'll take that further. Negative 1 over 6, negative 6.5 is in fact smaller than 0. So it's kind of like having a far point that is in a circle so far away that it ends up going around and backtracking behind the eye. Now, why do I say it that way? It's like having a far point that's beyond infinity. Now, the reason I say that is, what is it that our eye does when it reads closer objects? It squishes. And by squishing, it makes the radius of curvature larger, and therefore makes the focal length shorter, and therefore makes the optical power greater, which is the same thing that wearing a +6/5 correction does. In other words, in order to see distant objects, all her eye has to be able to do on her own is accommodate, which is what your eye does when it flexes and increases the focal power, the optical power of the lens. All it has to do, it's kind of like reading. You need reading exertion, if you will, on your eyes to take objects that are so far away and squeeze them in so that you can see them at infinity. Isn't that bizarre? So as long as she doesn't get too old and her ability to flex her lens and make the optical power greater, as long as that doesn't diminish her ability to accommodate, then for her, looking at a distance is like us reading, is like somebody with healthy vision reading. Isn't that crazy? Of course, it means that she's got to accommodate even more to see closer in. But even seeing at a distance, it means recipe for a headache. You know, when you read for a long time, your eyes get tired. Well, this individual has to do that just to see all the time. Hence, she was probably diagnosed as an infant, but hence somebody that had the same type of an issue would be going into the optometrist or the ophthalmologist and saying, gosh, I'm always getting headaches. Can't figure why I'm getting headaches. My eyes are always tired. Well, it's because your eyes are having to strain constantly just to see anything. Because optical power is too low. So you're constantly having to increase the power of your lens just to see at a distance. So she can see just fine. It just was a strain on her eyes to do so. So she wore glasses or contact lenses. Problem is, it's hard to diagnose. If you're farsighted and you sit down in that optometrist chair, as long as your eye can flex healthy, you're younger, then you can, when you look at that eye chart, it looks just fine. You got to strain your eyes to see it. Right? It's like reading. You see it just fine, like somebody looking up here. Problem? It's hard to diagnose. So what do? Put a little drop of anesthetic on the eye. They used to use cocaine. Now they use whatever else they use, lidocaine or whatever. And it numbs the muscles of the eye so they can't contract. So now your eye is fixed in its relaxed state. Now when you look at a distance, I can't see a damn thing. So So then you start flipping the little lenses in. Sure enough, by increasing the optical power, oh, it comes into focus. Which looks better, 1 or 2? Which looks better, 1 or 2? And usually they flip them backwards so that you don't fool yourself. There's all kinds of tricks and the bias when they're doing that little refraction process. But the point being, just that you physically are reading to see things at a distance. Now, back to this idea of accommodation. For the healthy eye, this is for any person, but for the healthy eye, as a starting point, to focus anything closer than the optical far point requires a process we call accommodation. So when you get older, that's where you lose your ability to accommodate. So your eye muscles, so they flex, increasing 1 over F. What they do. That's what we call accommodation. As you get older, you lose it naturally. Your eye muscles get weaker. Your lens gets more rigid. Kind of like think about a rubber band oxidizing, if you will, or rubber on the bottom of your tennis shoes. The older your shoes get, the more firm they get and less flexible they get. So that oxidation is happening with age. When that happens, it happens to everybody, so one thing you can't control, kind of like death and taxes, you lose your ability to accommodate. Old eyes, we call it presbyopia. You lose this ability. Now, just to give you a sense of it, when you are a child, your ability to accommodate is ridiculous. So I'm going to point out that 1 over F, and this is now the accommodation for a child, is oftentimes greater than plus 20 diopters.
Wow.
Yeah, well, I mean, you kind of think about it. You can see your food source at a centimeter away from your eye or some crazy distance away from 5 centimeters from your eye with focus. Makes perfect sense. Your eye is so flexible, you can see really, really close. They don't need to see things too far away. Children, especially infants, tend to be a little bit myopic. Is that right? No, they actually tend to be, I think they're hypermetropic. Start out hypermetropic. You can see things really, really far away, but you can also see things really, really up close. I guess maybe that's a fight or flight sort of thing. Get your food source, but also, in principle, you can see objects moving out as you're trying to absorb information and gain all of these motion and all these things. You can't process them, but your eye does. As you get older, with age, this value decreases. Functionally, to 0. If you live long enough, it's basically going to go to 0. That's why people need trifocals. Right? It's one thing to need correction to read. It's another thing to literally need eye lenses to see everything distance, middle, and close. Right? So trifocal lets you do all
I didn't know
three.
there was such a thing.
Yeah, oh, absolutely. So you can see your speedometer on your car with your middle lens. You can read up close with the bottom lens. And then when you look over the top, you can see, if you need it, you can see your distance. Or some people just keep 2 or 3 pairs of eyeglasses.
Why
One to
can't you
correct
just
for
have-
myopia, one to correct for middle, and one to correct for close.
Well, you just make eyeglasses that have lenses that are flexible, and you have a little knob.
I think that's a materials issue, because it would have to flex uniformly over all
Right,
sides.
there's some engineers in this room.
You betcha, there you go. But the big the grand solution, at least in the 80s, was to produce what are called progressive lenses. And a progressive lens has, if this is your base eye power for your correction, so there's your eyeglass lens. Now, a traditional bifocal would basically be inserting a little lip that has a greater rate or a shorter radius of curvature than the base lens. And if you have a need for trifocals, then you have something that's a little bit, it's still flat, but it's a little bit, this is way, way out of perspective. It's flatter than this, but steeper than this. So you get that sort of middle distance. So with improvements in manufacturing, what they came up with is something called a progressive lens. And a progressive lens, I draw this a lot bigger, is if this is your lens, let me draw flatter. If this is your lens, that's probably better. Then at the bottom, instead of it being like this, at the bottom it starts out really steep, and then like a parabola, flattens out to your base curvature. So when you look with your eye down here, it's reading. When you look with it somewhere in here, it's sort of middle distance. And you've got an even transition. Of course, your eye has to pick it up in your eyeglass, but you can literally focus on everything far way up close because it's a continuous curvature like a parabola.
Sure, you get used to where the sweet spot
Yeah,
is.
you always get used to it, given enough time. Some people like them, some people hate them. Well, yeah, so that's a progressive lens. So they've come up with solutions, but and that's probably from a manufacturing process the easiest because you use the same plastic, same material. You don't have to come up with something new and some apparatus to shrink and expand. What's that? And it's hands-free. You're not doing this when you.
Well, you know, there'll be something that'll be connected to your brain that controls it just like a muscle with a little electrical signal.
If Stephen Hawking could talk with his eyes, there's a way to make it work. Right?
He's to the point now where he has to have an assistant with him who interprets things.
Yeah, but isn't he doing a lot of that with his eyes? Isn't he got like a optical cursor on the screen?
He's got a person that reads him now.
Blinks.
Assistant.
You get old. I mean, that's what happens. We all get old a little bit at some point.
Grad
Yeah.
student, of course.
So let's just kind of get a sense. What is necessary if you've got a healthy eye to see things in what we would call comfortable reading distance? Yeah,
Be
about
able to
here.
bend your
How much does your eye
lens
need to accommodate to see something at about, usually the standard is 25 centimeters, quarter of a meter. Okay, if you can't focus to a quarter of a meter, I mean, that's healthy or comfortable to just read. Can't do that, you need eyes prescription. So what type of a correction would be necessary to take a healthy eye and be able to see that? First of all, what would be the optical power of an eye that has to focus a distant object at a quarter centimeter or a quarter meter? So again, these are just applied optics problems. There's no difference in these problems from any other thin lens problem. The only difference is you've got certain fixed constraints. And you're always adding something else to correct something or potentially correct something that otherwise you wouldn't worry about if you're just focusing an image of an object.
the optical power of an eye that could focus a distant object at. Ask that question again.
So we want to read an object or to focus, how about that, to focus an object. At O equals 0.25 meters. than 25 centimeters. One over F, and well, I'll just call it 1 over F. For this I would need to be 1 over O plus 1 over I. This is I for the I.
Makes the whole world one.
So we would have 1 over 0.25, which are 4 diopters, plus what we had before. I'll just use a healthy I. So we would need 59.56 diopters of optical power for our eye to be able to see. Or if you will, this corresponds to a delta F. This is just a read, if you will, of plus 4 diopters. Can't do this if you cannot accommodate at least 4. Now again, infants 20, that number degrades with time. Usually by the time you're 45 or 50, your ability to accommodate your delta F, this value here, this is what your eye does. This is the change due to accommodation. It gets less than this. So if your eye could only add, say 2.5 diopters to its relaxed normal state, then you would need 1.5 extra diopters in order to focus at this distance. So you don't have to read like this. So,
How far do you think my finger is from my?
what's that?
That's about as far in as I can still focus before that finger is blurry.
Use one eye, not two. Right, 2 eyes you cross and you get other issues, but you get one
Still.
eye and,
Still goes blurry after I get any closer than about here.
yeah, I'm right here.
Looks like about 25 centimeters.
25 centimeters? There's no way this is 25 centimeters.
Now, here's the thing, okay?
Yeah.
So, the assumption though is a relaxed iris.
You silly guys. I know. But I'm just saying, like, how much am I capable of bending my
Okay.
lens? This
So-
is 10 centimeters on the inside of here, so 25 would be like out to there.
10, 25, yeah, it's about right there.
I'm just trying to do the math.
Oh, so you're prematurely degrading your accommodation.
What I'm trying to say is, like, the maximum, if I'm looking at my finger,
I see.
the maximum that I can
It's
bend
like
my
that.
lens is like, 8 diopters or something like that. You know, at my age now, 30.
Inverse of already.
Well, if I'm looking at it and say this is 10 centimeters, right? Then that would be 1 over 0.1, which would be 10 diopters. If this is a little more than 10 centimeters, I'm maybe 8 diopters.
So you kind of see all these constraints to your eyesight. So the two conditions then. So a healthy eye needs plus 4 diopters of accommodation to read at 25 centimeters. Now, you may not necessarily read at 25 centimeters. You may actually read at 30 or a half a meter, right? But think about all the other things you have to do. Clipping your toenails, I don't know, whatever you do up close, tying knots, threading needles. Because of the size of the things that you're looking at, you've also got, you've got a resolution of your ability to see small details. So you want those up close. It's hard to thread a needle out here because you can't see the hole, right? So you need it close enough that you can see the hole, but if you have to get too close to where you can't focus it, then you're kind of screwed. You got to stick it down here and hope that you can still see that hole. So you've got all these issues, and we don't do everything at a reading limitation, right? We got other things that we do that sometimes require seeing closer. So kinds of problems here with this. So, but we just sort of use that as a standard. Now, a person with .25 diopters of accommodation ability. I'm going to call it ACOM capacity. Has the closest distance they can read is sure as heck not going to be 25 centimeters. Right? What's the near point of a person who can only accommodate this much? Nice thing is, again, we assume infinity is healthy, so you almost never have to deal with the 1 over I term. So O near, which is what we call the near point. It's the closest object that you can see. Would be 1 over 2.5, or give or take
40 centimeters.
40 centimeters. Meters. So in other words, you see out here. Now maybe that's okay. I mean, if it doesn't bother you, it doesn't bother you. But that sort of becomes the next issue is, okay, if I want to see up close, or I want to be able to thread needles or whatever it is I'm doing detail work as a hobby or something, painting, small, whatever, then I would need a reading prescription that would add plus 1.5. So the cheap thing is go down to the grocery store where they have those cheap reader glasses for $8.99 and pick up one that is the difference between 4 and 2.5. Or just live with it. The cool thing is sometimes myopic people can get away without reading glasses even as their eyes age. You had a -4 prescription. In other words, you were nearsighted enough that you needed 4 diopters of correction. You have to decrease your optical power by 4 diopters instead of increase it. Then your far point is 1 over 4.25. So you're already seeing up here. So you take your glasses off, you read comfortably. You don't even have to accommodate, and you can still see up closer, based on your ability to squeeze your lens. So that's kind of cool. Now, in order to see at a distance, you need to wear eyeglasses to look out. You just take your eyeglasses off to read. That's what a lot of people do. Because most people are myopic, so typically when you want to read, take your eyeglasses off. Unless you have enough of a disparity between your eyes. Yeah. So I've had like -3.75 in one eye and -4.25 in the other eye. So there's just enough of a difference. I kind of didn't like it, so I never usually read without eyeglasses. I just assume wear the glasses, balance my vision, or contact lenses, balance my vision, and then just strain.
So probably more of a biology question, I guess, but just for curiosity's sake. When you are flexing your lens more often, does that cause it to wear out faster? You know, because you're having to
The
bend
jury is out on that question. I don't know what the answer is.
or does it last longer? You know, it makes
Well,
it
it's a bit of a loaded question, okay? Here's why it's a loaded question. It probably doesn't improve or make worse the rigidness of aging on your eye. But you can improve the muscular capacity of the ciliary muscles around your eye. So there was an approach called, I think it was called the See Clearly method. It was like a physical therapy approach for the eye, optical therapy. And I don't know exactly what they did, but basically with healthy eyes especially, because it's easier with healthy eyes to start there when you're younger, you get closer to where it becomes an issue. And you basically exercise your eye muscles so that they get strong enough to fend off that accommodation longer. So you're less likely to need contact or reading glasses with age. Yeah, there's all kinds of things like this. It's kind of cool. Now, some hardcore optometry schools don't buy into it. I think the success is hit or miss. Just like, you throw somebody into a gym, they're not necessarily going to look like Arnold Schwarzenegger. But Pacific was really big on those types of optical therapy. Others not so much. So, I think it works at least to a small degree. Whether it makes enough to matter for some people to actually do it regularly, I don't know. It's about the muscle.
When it comes to getting LASIK, they are using the laser to shave something off of your lens.
Yeah, we can take a break now and just keep this conversation. What happens with LASIK is you've got this problem, your eye is too powerful because your lens is too strong. Well, what is it that is responsible for the majority of your optical power?
Right?
It's your cornea. Okay, the lens fine-tunes in the back, but your cornea that does most of the refractive properties. So they go in and they base well, and this is the beautiful part, is they cut away the little layer of mucousy tissue over the front of the eye. That's actually the hard part. Okay? That's where it's hit or miss. You screw that up, then you're going to be miserable for the rest of your life after having LASIK. Okay? What's that? No big deal. Well, the reason
I've
is
seen video of this. It's
you got to put it back.
frightening.
You got to put it back, and it's got to heal. If it doesn't heal right, if you develop scar tissue, or you don't cut it right and you inadvertently damage the cornea, then you've got issues with it. I had a great experience with it, and I had one of the better ophthalmological surgeons in the area by referral from one of my best friends who's an optometrist. But basically, you go in then and you